Hello and welcome to today's lecture in ISP. We are already in week 10, which means that this is today our last regular lecture. And yeah, our main topic for today is again data structures. But at the beginning, as usual, the organizational part. As I mentioned, we are in week 10. So today we hand out the weekly exercises 10 that are related to assignment 4 with the same deadline as the assignment 4 and the exercise 9 on 21st January. So still a bit time until then. And the reminder again that you have to pass at least 50% of the exercises to avoid point deductions for A4. Okay, so for the recap from last time, we have prepared a few quizzes for you, and the first one is a question about const in C, and you have to check all the correct statements about const in C. So already 32 answers. Let's wait a few more seconds. Maybe we can reach the 40. Yeah, got it. So yeah, most of you got the two right answers correct. So const can increase the readability and maintainability of the code, as we have mentioned last time, and it also prevents the modification of the value of a variable. So I can make a variable constant with the keyword const. Good. Next question is about this code snippet here. So what is the output of this code, which is related to our topic enums from last time. So we have here an enum defined and a main function that does something with this enum and prints something. And the question is, what is the output? Okay, let's wait a few seconds again until we reach 40. Okay. Yeah, so most of you got it right, but there are a few that thought the answer would be 3, but the correct one is 1. Why is that? So we have here an integer input with the value 7, and here we compute the modulo with color size. And color size is the last element in our enum, and our enum, since we didn't provide or set the default value, starts with 0, meaning that red is 0, green is 1, blue is 2, and the size is 3. So we have here the operation 7 modulo 3, which is then 1 in the end. Okay, next question is related to file I/O. The question again is what the output of this program is, and yeah, the content of the file gift.txt is Merry Christmas, as you can see here at the top in this comment. So you can assume that this file exists and that this is the content of the file. So what happens in the main, we have here an fopen to open the file for reading, then we have a nar check, then we perform an fseek operation, we declare here a character buffer, and then we call fgetS, and afterwards print the buffer. And in the end, we close our file. The question now is, what is the output?
Maybe to add fseek, file pointer 6 seek set. So seek set is always the current position of the cursor.
So let's wait until we reach 40 again.
Sorry, seek set is always the beginning. Yeah. Seek cur is the current position.
Yeah.
Yeah. But in this case,
Wouldn't make a difference.
wouldn't make a difference. Yeah.
Okay. Let's have a look. Yeah, and the
It's
answers
a tie.
were head to head. So it's Christmas versus Christmas with
The
this
exclamation
last
mark, yeah.
letter in the file. So why is just Christmas without this last letter the correct answer?
So the fgets reads size of buffer,
Which is 10,
10
in this case.
but the fgets always reserves the last character for the null byte. So it only reads 9 characters and adds the null byte. 9 characters from the C from Christmas means it reads Christmas, but does not read the exclamation mark in the end. That's why Christmas is correct.
Yeah. Okay. Bit tricky, but yeah. Fgets and ensures that there is this null byte in the end. Okay, and the last question for our recap today is a question about data structures, and you again have to check the correct statements here. So there's one question about arrays, one answer about arrays, one statement about linked lists, one about stacks, one about queues, and one about trees.
So the one about tree should be easy because we heard it the last half an hour in the practicals.
Kind of repetition from the last hour from our practicals. And the other ones are at least a repetition from our last lecture. So the first statement basically is about whether arrays can or allow fast random access. The second one is basically whether linked lists can grow and shrink efficiently. Stacks follow the last in first out principle. Queues follow the first in first out principle. And in a tree, the root is the top level node. Leaf nodes have no children, and siblings are nodes that share the same parent. 40 answers reached. So let's have a look. Yeah, all statements are correct. And yeah, you almost spotted all that right. Okay, then before we start with the topics for today, we just want to mention our Christmas special next week.
After the practical, so there will be a regular practical session.
Which is recorded as usually, but the lecture afterwards is the Christmas special, and it's not recorded.
Because we want to participate here, we do something special, and if you have time, it's very cool, so please come here and visit us. We maybe have short quiz, and it's kind of fun. So if you find time, please come.
Okay.
Okay, so then let's continue with the second part of data structures. We already started last time, and we have to, I think, continue with linked lists a bit.
Yes. So the first few slides are basically a repetition from the end of last week's lecture. So we can go over it very quickly. So we talked about linked lists with the example of a playlist of songs. So we had this screenshot where we have a few songs, where we have this playlist in general. And then we talked about what is a song. And then we said a song has a few attributes. We said at least there has to be an artist, a title, and the length. And then we said, we could define this in a struct with two character arrays and a short variable, and call this song. And then we said to create a whole playlist of songs, we could connect a song with the next song, and then the next song, and so on, as we can see here in this visualization with the arrows here. And so we have to somehow, bring the next song reference into our struct, which we did by adding a song pointer called next song in our struct. So if we have just one song in our playlist, as we can see in this example, then we do not have a next song, so the next song pointer then would be null. If there is a next song, then this pointer points to the address of this next song. And this next song then has no next song, so the pointer then would be null. So this is basically now the idea of a linked list, where we connect each song with the next song, and at the end of our playlist, there is no next song.
And when you already heard the practicals today, you might remember that the binary tree has 2.22 next elements, so the children. So the linked list is basically a simple version of a binary tree with just one link to one new element.
Correct. So it's a bit easier because we do not have, we can't go left and right, but we just can go to the next element. Okay, so this can then be, a playlist of two songs, where the first one links to the second one. And the first list operation for this linked list is the iteration that we want to have a look at. So we want to, for example, iterate through the whole linked list. So we want to, for example, print out all the songs that are in our playlist. So then we would start at the first element, go to the second one, the third one, and so on, until we reach the last one, and then our iteration is done. And how would we do this? Similar as we have seen in the practicals. So we start with not the root, but the head in this case. So we call the first song head, which is the start of our playlist. And then we always have a current pointer that we set always one further to the next and so on. So we start with the head, with the first one, and then to go to the next one, we set our current pointer to the next song by accessing from our current the next song pointer. So we then say the current is now the second one. And the third one in this case does not exist because we just have two songs here. So if we then go to this pointer, this would be null. So in the end, our current points to null, and then we know we have iterated through the whole playlist.
Okay, so how could we implement that?
Okay, let's have a look at the code. So this is a very simplified version. So we can, for example, have a function called iterate that does not return something, but for example, then print something. So we just have a comment here that means that we would print the artist and the title, for example. Yeah. So we just hand over our playlist head, meaning the pointer to the first song. This is our playlist head. And then, as we just have seen in the visualization, we start with current, which is a song pointer, pointing to this first element.
So basically we make a copy of our head,
yes,
which we now can use as an iteration pointer always.
Yes. Yeah. And we do the iteration as long as the current pointer is not null, because then we know we have a song that is not null, meaning that we have still a song. And what do we do with this song? For example, we can now print the artist, the title, the length, and so on. And afterwards, we have to move our current pointer to the next song, which we do with this statement. So our current is now the current next song. And then, we have again the check. And if again we have a next song, so current is not null, then we print this next song. And then we set our current to the next song. And then the current reaches null, and then we know we have iterated over all elements, and then this method is finished. So this would be an easy example of how to iterate through a linked list. Yeah, but iterating, to iterate through the whole list, we first have to have some elements, right? So we have to also have a look at the insert or add operation to create new songs and add them to the playlist. So for example, if we start again with this example that there exist already two songs, so this playlist, and we want to add another song to this playlist, how could we do that? So we could create this new song, so as we can see in this visualization here, but then we have to connect it somehow to our playlist. So in the end, so we start again with our playlist head, iterate through the whole playlist, and in the end, when we reach our last song that points to null with next song, there we want to add now the address of our new song. So now we know we are at the last element if we always check for this next song whether this is null. And if we reach this element where the next song is null, we know it's the last one, and there we can then say this next song should now point to our new created song. And then we have inserted this new song to the playlist, and so our playlist has one element more than before.
So there are always kind of two tasks. One is creating the new song, and the second task is edit in the linked list. They are kind of independent. One is creating it on the heap, for example, writing all the data in it, setting next song to null. And the second task is then my new song I want to add it at the last element or after the last element as the new last element. And this is basically just adding an address to a pointer.
Yes.
But of course, I have to iterate to come to the end. And then when I find the last element, then I can kind of connect them.
Okay, but now let's have a deeper look into that, what David just mentioned. So let's implement those functions in C so that we can create a new song, add this new song at the end of the playlist, and then also print the playlist. And yeah, let's do this step by step. So the starting point is, let's assume that we have already created 2 songs that form a playlist. So we have just a pointer called head to the first song. And then there's also a second song, which is connected to the first song in this linked list. So this is our starting point. And yeah, we implemented with our struct that we've already seen before with the artist title length and also this next song pointer, similar as before. And yeah, in our main, we now assume, as you can see in this comment here, that 2 songs have already been created, and there's also now this playlist that has, yeah, that is just a pointer to the first song, and then the first song has the pointer to the second song. So this is the starting point. So what we want to do now is, yeah, we want to create a song at first and then link this song to the playlist. So the first part is create this song, as we can see in this visualization here. So we can do this by writing a function called create song that takes, yeah, an artist, a title, and the length, so the data that our new song should have. And in the end, it returns a song pointer, so the pointer to this new song that we've just created. How does this work? So at the beginning, we allocate memory for this new song with malloc and the size of our struct. Then we perform the nar check, and afterwards we copy the data into the created song. So we copy the artist, the title, and also the length into our new song. And very important, as David mentioned in the practicals today, ensure that you also set the next song pointer to null, because if you do not, then we do not know what's the data in this location. So what data does the pointer have? And this could be a different location, different address, and something different from null, and then we would have a problem, because we would then assume that there is a next song at this address, and if we would access this address, yeah, we are not allowed to, maybe.
Just to mention, there could be one error here in this code.
Yeah.
Any ideas what could go wrong here? Yes? Yeah, so this string copy here could be an issue, because we actually don't know what this char pointer here and what this char pointer here is. So it could be the thing that it's not ended with a null byte. It could also be that it's larger than my defined character array here. So it would be better maybe to use here an arbitrary length. So whatever string comes here, we have to check it, or we have to allocate memory for this string length and then use just a string pointer here. Or we have to somehow check if this is a valid string by, for example, calling string line. If string line is less than 50, for example, then we copy it. Otherwise, there's a problem, whatever.
Yeah. True. So keep in mind that this implementation that we show you now is a very simplified version and just should give you an idea of how linked lists work. But there are for sure, or there could be for sure, some edge cases that we now do not consider because, yeah, this is just a simplified version to give you the idea.
Okay, and when I want to call now this function, let's say in the main.
Yeah, I can do this by just calling the function, create song, passing the arguments, in this case, the data for this new song. And yeah, since we return the new song here, the song pointer, we store this here and perform the null check.
Yeah, so
if this now goes wrong here, so if it is null, we would have to free the whole playlist before we end our program. So this is just a comment for now, but we will also implement this later. Okay,
Yep.
So let's just keep it as a comment for now, but we would have to do it for sure. Yeah.
So until now, we created the song, that's the first part, but it's still not linked into our linked list.
Yes.
It's just somewhere else, but it's not connected to our list. So we had to add this as a second step.
Yes. So the next step is then to add this created song to our playlist. And how does this work? So now we have to start again with the playlist head, iterate through the whole playlist as we have just discussed before. And as soon as we reach the end of our playlist, we now can add to this last song the value of our new song to this next song pointer. And then the last song in the playlist links to our new song. So now we have added this third song to our playlist, which is now the last song in our playlist. So this is the idea. And how can we do this? We now implement a function called add song to playlist, which is basically just void because we just want to add it, but we do not want to have any result out of this function. And yeah, we again pass the playlist head and for sure the new song that we want to add. At first, we perform null checks. So if the playlist head is null, so there is basically no playlist, we could return the new song maybe as then head of the new playlist. We could do this, so it depends on how we define our use case.
But in this case, this function just assumes that there is already a playlist.
Yeah, correct.
So if playlist head is null, then this is wrongly used and it just return.
Yeah, correct. And if the new song that we pass here is null, then there is no new song, so we do not have to add a new song, so we can just also return in this case. Yeah, then we start again with our playlist head and again create a current pointer, which is just a copy again of our pointer pointing to the head for the iteration. Again, which is again checking whether not the current element is null, but whether the next song pointer of the current element is not null. So if it is not null, then there is already a pointer to a next song, so I'm not at the end of the list yet. So I have to go to the next song, so setting my current to the next song. Then I perform this again until I reach the last element in the playlist. And then this last element has a next song pointer pointing to null because it's the last element. And then I have done this iteration and then I have my current pointer to the last element. And for the last element, I then set the next song pointer to the new song, meaning that this last element points to the address of our new song. And this is all I have to do to insert this new song to the playlist.
Let me just add one thing.
Yes.
When you paid attention to the practicals today, we had some kind of a similar problem, iterating in this case, what was the binary tree, but we used a slightly different approach. There, we remembered the previous node and the current node. And in this case, we don't need the previous node, but we look one step ahead always of the current node. And if the next song is null, then I should stop at the current node, so I still have a current node always valid, because it stops when the current next song is null. Another approach, both are completely valid, would be to say while current is not equal to null, and always remember the previous element, both working.
Yeah, true. So this approach is, I think, easier to implement for a linked list than for a tree, because here we just have one next pointer. In a tree, we have
two,
at least two. When it's a binary tree, we have two. Otherwise, there would be more. So yeah, with just one pointer, it's easier than for sure to implement it this way. Okay, and now we can call this function in our main. Yeah, by just passing the playlist head and the new song that we've just created. And playlist head, this is, as I mentioned before, as we just assume the first song in our, so the pointer to the first song in our playlist, which is the playlist head. Okay, so now we have added a new song to the playlist, and now we want to print the playlist, for example, and we can do this with this function called print songs, taking again a song pointer, again the head of the playlist, so that we can iterate through the whole playlist and print each song. We again use a current pointer starting with playlist head, and as long as the current pointer is not null, we print all the data of this current pointer, so of this current song, starting with the first song with the playlist head. So we print artist, title, and length, and then we set our current to the next song. And if this is not null, we again print this next song, and so on and so on. And yeah, when we reach the end of the list, the current is null and the printing is finished.
So as you might see, this while loop occurs maybe in all of the linked list operations. And it's very important to understand this while loop, because we had it at the add, we have it now at the print. So always when you want to iterate over all of the elements in the list, you somehow need a loop to refresh a pointer and come to all of the nodes or all of the elements. So you should really try to understand that concept of iterating over a list or a tree or whatever, because that's, I would say, the first step and the most important step to understand how this works.
Mm-hmm. Okay, and before we have a look into the main again, we now also implement a free memory function that frees the whole playlist in the end of our program. So this function could look like this, again taking the playlist head, again, creating a current pointer, again iterating over the whole list until we reach the last element. And what we do now is, we want to free all elements. But here we have to consider to not free the current element.
Why? Any ideas?
What could be the problem if I just iterate over the whole linked list, and when I'm at the current element, I free this current element?
Yeah, so
Correct.
We lose kind of the access to the next pointer because we are still need the pointer to the next element. But when we free this memory before, it might be that it works still because free does not clear this memory, but we don't know. So we definitely will have an uninitialized access. So we have to somehow store this temp variable first, or this current variable first, to get access to the next song. There are again different possibilities here. I could also store the next song in a temp variable to So there are different possibilities.
But yeah, the idea is basically the same as in the practicals with the second pointer with the previous pointer. So we, here create a previous pointer, so to speak, which is called temp in this case, pointing to current, and then we set current to the next element to have this previous pointer. And then, since we then have with current a pointer to the next song, we can free this previous song, which is in this case called temp. So this is important to not free the current, but the previous or temp one.
So if we put this now all together, so creating a song, adding the song to the playlist, printing the song, and freeing the song, how does it look like?
Yeah, just calling all the functions that we've just implemented. So in the end, printing the songs and also free the songs, and always passing the playlist head. And now we can also call this free songs here in within this if statement here, because this was just commented out at the beginning. If the creation of a song failed because, for example, there is no more memory, then we get a null back, we have this null check, and then before we want to exit our program, we want to free all the songs, the whole playlist, which is created before, and we can call this free songs here to do this.
Okay, so we added songs, we printed it, iterated over it, free it. There's another possibility to kind of work with a linked list. I want to maybe also remove elements from a list.
Sure. So the next linked list operation would be to remove an element, and we do not go into detail for this operation, but we now have a look just at the visualizations to get an idea of how this could work. So we have the same example as before. So we have a playlist of 3 songs, and we now want to delete an element inside of the list. So for example, this second song here. So how could this work? Again, starting with the playlist head as current element and iterating over the linked list until we reach the element we want to delete. So this could be, for example, by checking for the name, for the title, the artist, and so on. And then we reach this point where we get to this element that we want to delete, which is called current. And as you can see, as similar as in the practicals, we store a previous pointer. Okay, so we always have a previous pointer to the previous element and a current pointer to the current element. And now what we can do is just saying that the next song pointer of the previous element is not the current element, but this song. So the address of the next song of the current element, so that this pointer now points to the third song. So this is basically the idea, to just get to this element you want to delete and set the pointer of the previous element to the next element.
And this is the most important cool thing about linked lists.
Yeah.
Because when you remember what are the disadvantages of an array, when you remove an element inside the array, you have to shift all the elements after that to the left and then remove the last one. That's a lot of operation.
This was basically the motivation last time that we have shown with arrays for these data structures like linked lists. So this is a huge advantage from linked lists to easily add or remove items wherever I want.
Yeah, so this is just maybe changing one pointer.
Yes.
And
so just iterating and changing one pointer, and for sure, freeing the memory of this element. So we want to completely remove it from the playlist and remove it from the memory for sure. So we have to free this as the last step, so to speak. And in the end, our list now has just 2 elements. So this first one points now to the third one, which is here now the second one. So we have just removed one element in the middle of our list.
There's one special case. What
Yeah.
if we want to remove the first element?
So the first element, so if we want to remove the head, so the first song in this case, yeah, we would start with the head and we would then want to have the head pointing to this element. So we again would have to have a previous element pointer pointing to the previous head, and we would just have to free this previous head element, this first one. So then, yeah, there is no pointer to this one, but just our new head pointer. So we just have to free the previous head and, yeah, set the new head before the freeing to the second element, which is then our new head.
One important thing to mention, as you might have seen, we always use the head. So as soon as you lose the head, you lose basically a complete linked list.
Yes.
So always keep that head. And that's why we always making copies of it when we iterate over it. So it's basically a kind of a convention to make a copy of the head, because maybe you need the head in the future, or most likely you will need the head in the future. So always make a copy when you iterate over it, to always keep a reference or a pointer to the beginning of the linked list, because that's the key. Otherwise, you lose the whole list.
Correct. Okay. Yeah, but how could we now really implement this remove functionality? This is something you have to do in the weekly exercise. So yeah, you have to delete a song from a playlist. So this is your task for the weekly exercise. Okay, so now we have looked at iterating over a linked list, inserting or adding elements to the list, and also, at least in a theoretical way, the removing of elements of a linked list. So we have already discussed a few advantages and disadvantages about linked lists. So the first, as we just mentioned, the advantage is the dynamic size. So in contrast to arrays, where we always have to specify the size of an array, for linked lists, they can grow and shrink dynamically. So we do not have to specify whether we want to have a playlist of 2, 10, or 100 songs, as they can grow dynamically. Also, it's very effective if we often insert or delete items, as compared, for example, to arrays. But there are also disadvantages, because if you compare now the implementation that we've just shown to, for example, arrays, so the access is maybe a bit slower, because if we want to have one song on a specific number in our playlist, we have to iterate through the whole playlist. And if it's the last song, we always have to iterate through the whole one. And for arrays, since they are stored continuously in the memory, it's a very fast access to go, for example, to the last element of an array. So there are also disadvantages. But so you have to decide based on the use case which data structure fits best, depending on the operations you want to do with the data. Okay, so now we have seen the linked list, and now we also want to show you further data structures, and we start with the doubly linked list. And this is basically the same as the linked list with one additional thing. And this is basically, besides having the data, for example, the artist, the title, the length, and the pointer to the next element, having a pointer to the previous element. So now we do not have the pointer to the next one, but also always to the previous element. So why would we have to do, or why do we want this?
So sometimes I just want to go one step back and not always start from the beginning and iterate to find a certain element. Sometimes I need this two direction. It's just easier and faster.
Just imagine some streaming platform where you have some playlists and you listen to a song and now you want to go back to the previous one. So this is, for example, a good use case for doubly linked list instead of just a linked list, by always just having the next song and not the previous song. Okay. Yeah, for sure there's a bit of an overhead, and yeah, we have to implement more because now we have also a previous pointer that we have to keep track of for each element. But as soon as we have implemented it, it makes it easier and faster to navigate. Okay. Then we finally come to trees, which is the last data structure for today. And as a repetition from last time, we just have again a look at this overview, also a repetition from the practicals today. So this is basically a tree with a root tree at the beginning, with child nodes, with a parent node for those two child nodes here, with leaf nodes, which are nodes that have no children, siblings that are nodes that share the same parent, and maybe an important thing that we'll have to consider later when we have a look at a specific implementation is a subtree. So you've already heard it today in the practicals that, for example, we can consider this tree as a subtree having D as a root node of this subtree. So we can look into this whole or we can have a look at the whole tree having here the root, but we have many subtrees here with different roots then. So this is maybe an important thing that we will need for our implementation later. Okay, but now we come to binary trees, which is which are special trees that have at most 2 children for each parent, which is also which you have already seen in the practicals today, which was also a binary tree there. So this would not be possible to have 3 siblings. So you can just have 1, 2, or none. Okay. So this is basically the binary tree.
Yeah. You already talked about that
yes.
in the last slide, so I think we can skip that. And
okay.
Also this one is just,
I think this is just a
another
definition,
definition
how the nodes are called. And now we want to have a look at the implementation. So we could implement a binary tree, for example, a tree of persons like this, that we have a struct person with just a name as data. So we could have for sure more attributes here, but we just go in this simple example with a name. And then we have pointed to a left and a right child, similar as in the practicals. And for example, in our visualization, this could look like this. So we have here Elizabeth. Then as a left child, we have Charles. Then we have as a right child Anne. And this, for example, goes on with left child of Charles is William and right child is Harry. So for this binary tree example, it would not be possible to have more than 2 children. Okay, and what are use cases for such binary trees? So as you have seen in the practicals, there we have had some kind of sorted binary tree where each node
is a number.
And the whole tree was sorted. And this is also used for having effective data structures sorted by their values so that we can effectively search, for example, or sort data within this tree. Yeah, and there are use cases, for example, in dictionaries or file systems where you can use such binary trees. Now, let's have a look at the implementation of the previous example that we've seen in the visualization. So with those 5 persons that are linked in this binary tree.
Yeah, and this is where I stopped Michi today in
Yes.
the practicals, because we now want to go through that step by step. I know it's late, but please pay attention to this one, because now it's getting important. How to search in a binary tree, it's not that easy, to be honest, yeah? Because we're using recursion for that. But as I think we try to visualize
Yes.
it in a easy, understandable way. So in this case, we have this tree, Elizabeth, Charles, Anne, William, and Harry. And we created one function, which is called find person. And we want to find Harry in our tree. How does this look like? How does this function work?
Okay, so this is basically the find person function that takes the root node, which is at the beginning for sure Elizabeth, because Elizabeth is the root of this binary tree. And it takes a name, so the name for the person that we are searching for. So in this example here, we are searching for Harry. And how does this work? We now go step by step for each statement. And we also, as David mentioned, try to visualize this, that you can easily reproduce it with the slides. And yeah, so we go step by step. The first one is we start here. And one remark at this point is that we below here have, yeah, the functions that we have just called as some kind of function stack. So we start with the main, and we now called find person with Elizabeth as root and Harry as character pointer that we want to find. So this is basically the start. And now the first check is whether our current root is null. So our current root, as we mentioned, is Elizabeth, so this is not null. So we can skip this and go to the next if statement, where we compare now the name of our current root, so Elizabeth, with the name we are searching for, Harry. Yeah, and this is for sure not the same, so we have not yet found Harry.
Now it's getting complicated.
Yeah, so and the next thing we want to do now is to search the left and the right tree. So now we want to consider the left side from Elizabeth, starting with Charles, as separate subtree. And afterwards, we want to check the right one as a separate subtree, if necessary, if we haven't found Harry until then. So this is basically the idea. So now we want to say, we want to find a person where Charles now is the root. So the root of
we are calling
subtree.
the same function again,
So,
which we are currently in.
This happens here. So the next step is we're calling find person, so the function we're currently in, but not with Elizabeth, but with Charles. So with the left child of Elizabeth. So this is now for this call, for this next call of find person, our root. And for sure, we also pass the name we're searching for, which is
Still
Harry.
Yeah.
Sure. Okay. So now we have called find person again, that we can see here down below. So still not finished the previous run of our find person iteration. So now we are again in a new find person call. And now, as you can see in this visualization, Charles is the current root. So now we are basically calling this find person on another tree, so which is basically a subtree of our original tree. Charles is now the root, and we do basically the same. So is our current root null? No, it's not, because it's Charles. Is the name of our current root Charles? Harry? No, it's not. So still haven't found Harry. So our root is again not Harry. So what do? We now again go to the left side and call our function again with the left tree. So again calling find person here, one step back, find person here, with the left child of our current root. So current root is Charles, left child is William. William is now the new root of the next find person call. Harry is still Harry we are searching for. So the next call, as you can see here, is now with the current root William. So again calling find person with another subtree. Again checking whether the current root is null. No, it's not. It's William. Is William Harry? No, it's not. So what do we do then? Same as before, calling find person again for the left subtree of our current root. So the left side of William. Meaning that we call find person with the left child of William. What is the left child of William? It's null. The name is still Harry. So calling again find person with our current root. So the current root, as you can see on the left side below, is null. Now we check whether the current root is null. Yes, it is. So we arrived at a leaf node, obviously, where there's no further child on the left side. So we return null because now we haven't found Harry. So returning null gets us back to our previous call of find person, where William was the current root. And now we are here, and find person with the left subtree of William returned us null. So we perform now the null check. Whether it is not null, no, it's not. It was null, so we haven't found Harry yet. So what do we have to do now? We have to check the right side of William. So now we call find person again, similar as before, but now for the right child, which is again null for William, and the name is still Harry. So for the right subtree of William, we now check whether root is null. Yes, it is. So we arrived at the leaf node again and return null. So still haven't found Harry. Okay, so now we check the left and the right subtree of William. Haven't found Harry. So what we return now is what we have got back of the find person call of the right subtree. We do not need to perform a null check here as we have performed for the left side, because no matter whether it's null or not, we just return this value. Could be null, could have been the person. But the check is then done at the previous find person call, which was the one where Charles was the current root node. And remember, we just now are back in this call where Charles was the root node, and we performed the search for the whole left side of Charles. And we did not find Harry yet. So this is again null. It was null, the left side. So we go to the right side of Charles. Again calling find person with the right child, which is Harry. So now we are again in find person, a new call of this function for Harry. Now we check again, is Harry null? No, it's not. Is Harry Harry? Yes, it is.
Finally.
So finally found Harry. And since we have now found Harry, we do not have to check for the children of Harry. We can just return Harry here, so the pointer to Harry, which is the current root. This is what this function call now returns. Back to our previous function call where Charles was the root node. So now we got back from the right side of Charles in found P, the pointer to Harry. And this is what we return in this find person call now. So now we are finally back in our initial find person call where Elizabeth was the current root, and we checked the left side of Elizabeth. And what did we get back from the left side? The pointer to Harry, because we already found Harry. If we wouldn't have found him, we would have got back null at this point, and then we would have we had to perform the right side as well, which is not necessary because we got him back to the null check here, and then we do not need to perform the find person on the right side and return this pointer to Harry.
Finally.
Done.
Okay. 2 comments from my side. First, please draw your binary trees or linked lists. As you can see, it's much easier to understand because looking at the code as soon as you have recursion is very, very hard to understand. So try to draw any sketch, whatever, but it's a very, very good tip to try to draw it because, and always have kind of a pointer to your current root or whatever. I really use pens to pointing to all of my current roots. So the first thing here, and the second comment is you're getting very confused how deep you might be in the same function 3 times, 4 times, whatever. So always also keep kind of track how many calls you already had to this current function, because then it's also easier to track. And in some IDEs, for example, they print the call stack, so all of the functions you're currently in. And in this case, you would have seen main, find person, whatever. So that's also a hint to see how deep you're currently in the recursive functions.
Yeah. And as you can see, the solution, so the code for this problem is quite short and nice, but yeah, the execution of it could be a bit complicated.
And
but
also the understanding.
Yes,
yeah.
Sure.
So it might be that you at some point exited from knowing what we do here. No worries. It took me like months to understand this. Really, it will take you also some time to understand it, but at some point it hopefully make click, and then you get it.
Okay, so what can we do with trees? So here's an overview. We can search in trees, we can insert nodes into trees, we can delete nodes from trees, or we can sort or restructure in general the nodes in a tree, as you can see with this simple and short animation here.
That's basically converting a tree to a linked list.
Yes.
By restructuring it, and it's still sorted.
I think that's a very nice conclusion for our topic, data structures. And yeah, for the last few minutes,
we have 2
today.
Yeah, let's say selected topic. It's a very good word. Just 2 additional remarks for the final lecture, which you might have already seen somewhere in the lecture or in the practicals, might use in future courses.
Mm-hmm.
So yeah, one of is static.
Yeah.
We not really mentioned static.
Yeah. So what is static? We showed this now with a simple example. So the first example here on the left side is that there is no static variable in it. And yeah, as we know, if we have a function here and we have here a local variable and we print this local variable or increase it first with a pre-increment, then after this function call, this local variable is already freed. And if I call this function multiple times, it gets allocated again and again, and then in the end, the memory is again freed. So yeah, the output of this program would be 1, 1, 1, because we are starting always with a new local variable, initializing with 0, with adding it to 1 or adding by 1 and printing it. Now I've changed this example here on the right side to just adding static to the variable count here. And what this does is it outputs 1, 2, 3. Why is that? Again, we have here 3 function calls of this function. And yeah, as you can see, we initialize the variable with 0 and again add 1 to it and print it. But the output is now 1, 2, 3 because we have set it to static. What static does is it initializes this variable just once and
remembers it maybe?
Yes, so the variable is not destroyed at the end of the function call. So it's still alive after the first function call. If we then call the function again a second time, then we do not get a new variable, but we work with the old one that still exists. So this is basically just a variable that is initialized once and alive until the end of the program, and not until the end of the function. And it for sure keeps the value. So in this case, at first it is set to 0, then set to 1, we print 1. The second call, it is not set to 0 because it already exists. So this line is somehow skipped, so to say. So we work with 1, which is then updated to 2. We print 2, and then it's updated to 3. So count in this case exists once until the end of the whole program. Another example would be to have a static variable here in this function and returning the pre-increment of this variable. In this case, I called static example, this function, and I get back the value 1. Store this value in a local variable in the main, add 41 to this variable, print this variable, and then again I call static example and print the result. And now the result is 42 at first, and then it's 2. So this example should show you that here we get just the value of the static variable back. We store it in a separate local variable, and whatever we do with this local variable has no effect to the static variable here.
Because it's a copy.
Because it's just a copy of the value that I get back. So if I call then static example again, we are working with the static variable that has already been created in the first run, which has been set to 1, and now it's set to 2, and I get back this value and print it, so the output now is 2.
There's one question.
We'll come to that in a second, but let's have a look at a third example, which is again here in a function, a static variable. We set this to -1 in this case, and then we return not the value of the variable, but the address of the variable. We call this function, store this address in an integer pointer, in this case, and yeah, set the value then to 2025 and print the value that we get back from, again, this function. So what happens now? We return, as I mentioned, the address of the static variable. So the output is 2025. So what happens here is that at first this variable is initialized to -1. Now we do not return the value, so a copy of this value, but we return the address to our static variable and keep it in our local variable value. Now we set the value of this static variable, because we have the pointer to it here, to 2025. And if we now call again this function, this line somehow doesn't get called again, so we do not initialize it again because it already exists with this value. And again, we return just the address of our static variable, and we print the value of it, which is 2025. So this example shows that you could return the address of such a static variable because the lifetime of it is until the end of the program. So never do this with local variables that are not static, because the lifetime ends at the end of the function, but not for static variables, right? But this is some kind, and I think this is related to your question, this is some kind of a simulation of a global variable, because I create a variable here in a function with a lifetime until the end of the program, and I can, play around with it when I return the address out of it in my whole program. So this is some kind of a global variable, and this is forbidden in ISP. So do not use global variables or such a workaround, so to speak, for global variables in ISP. We just wanted to show you this concept of static. So it's possible to have static variables, as shown in the first two examples. It's totally fine to do it also in ISP, but not returning addresses of static variables out of functions.
Yeah, and just to add to your question, what's the difference between a global variable and a static variable? On the left side, for example, it's just the scope. So on the left side, you can use this variable, static variable, only inside this function. So the name you can only use inside the function, but you can use a global variable everywhere. That's the difference.
Okay, to sum it up, as I mentioned, it's just initialized once. It keeps the value between multiple function calls, as we've seen in the first examples. It's not destroyed until when the function ends, and the lifetime is until the end of the program. And use cases are, for example, to count how often a function was called. Maybe this could also be a use case for recursion, as we've talked before. And maybe if you want to call the same function again and again with the same parameters, but you want to get different results out of it, then you could also use static. Okay, and the last concept for today that we want to show you is function pointers. And we start with an example again. We have here a function called add, which basically just adds two integers and returns the result. And in the main, we now have a function pointer.
Looks odd.
Yeah. So important here is the data type that has to be the same data type as from the function, and also the parameter that we have here, integer and integer, that we have here without any variable names. So this is basically just the signature of this function pointer. And we call it, in this case, func pointer. And this is now a pointer not to an integer variable, for example, or to a struct. So it's a pointer to a function. And what I can do now is I set my function pointer to my function add. And now I can call function pointer, pass arguments to it, similar as if I would have called add. Okay.
So it basically is an alias for another function.
Okay, but why would we do this? Here's maybe a better example where we have more functions like add and subtract and a general function, so to speak, that is called calc. And this calc takes x and y and also a function pointer. And then this calc does the operation, which is the function pointer. So it calls the function that I pass into this function. And also, passes the arguments. So what I can do now is I can call this general function called calc, pass some arguments, and the last one is a function. So I can say do add at the first time, and then the second call I want to call subtract of those two values. So it takes basically a pointer then to those functions that I pass and calls those functions.
Yeah, that's very confusing, we know, and you will not need it for ISP, don't worry. But you will need it for future courses. Somewhere they might appear, and it's not that big deal you might think now. Basically, it's just a function name is just a variable pointing to not a value, but to a function. That's it. The syntax is pain. Yeah, but it is like that. It's C.
Okay. So we can conclude that by saying that it's a pointer to a function. It stores just the address of a function. And I think the advantage is that we can now perform a function selection at runtime. So at runtime, we can, for example, decide whether we take this function or that function. And here are a few use cases. As David mentioned, you won't need it in ISP, but maybe in further lectures. I think that's a good conclusion here. And I think we are also in time.
And at the end. Maybe we switch
lecture
to slide number 5 once more to remind them to our Christmas special.
Again, so please come to the lecture hall next week. The practicals are recorded, but not the Christmas special lecture.
Who of the two are you, the lecturers?
So I think regarding the beard must be the right one. Okay, so it's not really the end so far. So there are a few steps to do. So maybe practicing, exploring, failing, and also successing in the end, hopefully.
Let's hope it's successing,
And registering for the exam via TU Graz online, and also the most important thing, have fun with programming.
Yeah. So thank you very much for coming here each and every week. We appreciate your attendance. Good luck for the assignment. Good luck for the exam. If you have any questions, as always, you can contact us on Discord. Thanks again, Lucas.
Thank you, David. Thank you all for coming. And
hopefully see you next week
to
the Christmas special. Thank you.
All the best. Thank you. Bye.